Hello everyone, welcome to week 8 of these TA sessions. So this time the topic that was covered was clustering, K-means clustering and hierarchical clustering. So if you have any doubts regarding those topics, you can discuss those doubts. Yeah, I'm not sure about the exam pattern because we are not involved in creating the exam questions. Yes, at least the session is ongoing, so if you have any doubts, you can discuss.
Audible, sir?
Yes, yes, you're audible.
Okay, okay. Can we ask the questions from the previous lectures? The,
Yeah, sure, we can discuss that.
okay, okay. Some points I noted down. Let me see. Uh, on on week one, the slide number 21.
Wait, let me print the slide.
Yeah, yeah.
Week one, slide 21.
21, 21.
Designing a learner.
Yeah, yeah, yeah.
Hmm.
Yeah. Uh, see, there's a learner is there, and
Yes,
the reasoner. The see, we will learn, then finally we'll predict. Okay,
hmm,
as a model together. Okay.
yes.
So why it's called separate the reasoner? What is the role of reasoner? Or is really that component is there? It's like a indication only.
So, learner will learn some model, right? To you will learn the relation between your input and output. So, but then you will have to evaluate it whether the model you have learned whether it is keeping the answers that you require. So it will depend on the task at hand, whether you have a classification task or you have a regression task, right? So with respect to the task, you will have different reasoning. Like if you have a regression task, you want to minimize the squared loss. If you have a classification task, you like to increase your accuracy. So the reasoner is the evaluation part of the model. Learner is just learning the model, and reasoner, it tells how good your model is, or whether whether it is aligning with your task at hand. So that's why. So in general, we include these in this whole model that we build. But reasoner learner is the model that you have, and the reasoner is the part where you evaluate your model, whether it is performing according to the task that you have or not.
So finally, the we will call it say the component is more meaningful is the reasoner than the learner. Once learner is over, finally the model is called like a reasoner, then the learner. Am I right? Deployed system.
No, no. I mean, so suppose you are talking about linear regression, right?
Hmm.
So in linear regression, you can have any line as a model, right? So, but you will take the line which minimizes the loss. So then, how did you get that line? Because that line is the one that minimizes your loss, right? So how did you know that this minimizes your loss? Because of this reasoning part. So learner will just output some function, and it is up to the reasoner to see if this is the output or if it is a model that we want or not.
Okay.
Is that clear?
Yeah, yeah, okay. So reasoner will use for the finally the fitting for the hyperparameters and all this, and
Yeah.
finally make the perfection of
So
the
reasoner
minimum.
is basically the evaluation part that we.
Okay. Okay. It's indicating the evaluation part basically.
Yes,
Ideally,
yes,
you're indicating this is a part of the next phase, the evaluating the model.
yes.
Okay. Yeah.
So Jitendra is asking unsupervised learning. Unsupervised learning can be used in classification and image. That's why option one assignment option were not selected as relevant. So can you explain what is Jitendra? Can you explain what do you mean by what is this task that you have? Okay, which question? Okay. Yeah. No, you are not audible. Okay, okay. So you mean question number 13, right? Which says which is a true or false type of statement. So unsupervised learning cannot be used for classification task exactly because whenever we talk about classification or regression, then you need to have some specific labels present, right? Say, I want to classify some image into whether it is a car or a bus, say. So even for regression, you need to have a certain value that you want to compare against. That you want to get your output to be the as similar to the value as that as a label. But when we talk about unsupervised learning, you don't have any labels present. So you cannot exactly use unsupervised learning for classification tasks. Yes, you can get some idea of the patterns in the data, like if you have some car images, some bus images, so they will cluster together. You can just say that okay, this is one type of data, this is one type of data, but until and unless you have the exact labels present, you cannot learn classification task. Yeah, if your labels are present, then you can say that most of the images in this cluster belong to the class car, most of the images belong to class bus, but for that you need to have labels present for that. Is what's what's
Sir, in the week one again, slide number 77.
okay?
The limited features can lead to the noise. What is that? I didn't understood actually. How the limited features can make the noise.
Oh, okay. So suppose let us talk about. Okay. So first of all, let me answer this. So suppose you're talking about some data set where you don't have much features present. So let me talk about. Suppose you're talking about a housing data set, right? And in the housing data set, let me. So suppose you are talking about the housing data set. So suppose you have only two features like uh, length of the house and the breadth of the house, and you don't have any more features. So uh, it may be that even if two houses are of similar length, they may have suppose there was some features, they may have different age, right? So but if you don't have the age, you only have these two features, then your data will be susceptible to noise, right? So suppose you have one house of length say 50 feet, one breadth say 60 feet, and another say 51 feet, and another say 62 feet. So if you don't have this age parameter, age as a feature, these two houses will have similar output, like same regression value or something like that. But if you include the new, say suppose this is 30 years old, suppose this is 100 years old. So if you are trying to predict the price of this, then you will have more information. So you will have more knowledge about whether what will the price of each of these house. So the less number of features means you'll have more noisy type of data. More features means you'll have more information about the data. And if you have more information, that is you have less noise in the data.
What I understood. Okay. If I have limited feature, one is I am biased. That one problem.
Uh, I did not get you.
The moment I have limited features, if I don't consider all the features, I will be biased. The bias issue is there. If I take only few features, am I right?
Yes, 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 yes. You
Okay,
might
that's
say
all.
that.
Yeah,
Yes.
one part. Second part, it actually the limited feature will not add the noise, but I can't eliminate the noise. Like that, can I
Yes.
tell? Because I'm not adding the noise, but I can't eliminate the noise.
You do not have much information, so it will like both of these will give the same value, which is not true actually. So
Yeah.
more information you have, you can have more uh, better output, better classification or better regression in that case.
But can can you able to say that like if I have limited features, um, that line, no, that's what I got confused. That line is telling that okay, if you are limited features, the chance of your identifying the noise is more. Like that, I should interpret. Am I right?
Yes, yes, yes.
Okay.
So if you have limited number of features, your data may look like noisy. Your output will be biased towards similar data points because you don't have much information.
Okay. And can you able to can you explain to us a little bit on batch and stochastic
Okay,
this one,
gradient descent.
no?
Batch
22
and
and 23.
okay,
Yeah.
so batch and stochastic gradient descent, right?
Yeah. That how the minimizing the error, no? That part.
So stochastic gradient descent is like SGD. So whenever you have a data, so suppose your loss function is like this, right? So this is your loss function. Suppose your loss function is something like uh, summation, let summation yi minus your, so yi hat is your predicted label and yi is a true label. Suppose your loss function is something like this. So if we plot the loss function, so it will look something like this that we have shown here. So this y hat, we get this, maybe we are doing some linear regression type of thing. So suppose this is w transpose x. So here your w is the parameter that you have to learn. You have to learn w, right? So this loss function becomes a function of w. As you vary, as you change w, you will get different loss. And you want to get to the point where you have the minimum loss. You want to find the weights where you get the minimum loss. So suppose now if we do batch gradient descent, what it will do is it will compute the derivative of this loss with respect to all of the points. And so your gradient descent output or update is given as like this. So suppose you are at the TH iteration. So your weights at the t plus 1 iteration is weights at the TH iteration minus some learning rate into the derivative of the loss, right? So suppose you are doing a batch gradient descent. In that case, you will compute this loss with respect to all of the points, all points, that is x1, x2 up to, suppose you have say n points. So this is your batch gradient descent. And if you are doing stochastic gradient descent, your this will be computed with respect to 1 point at each iteration, 1 point at a time. So which point you are, so at each iteration, you will randomly sample a point. You compute the gradient according to that point, and then you again sample another point. You compute the gradient according to that point, and so on. So this batch and stochastic gradient descent differs in how you are computing this gradient that you have here. Is that clear?
Yeah. And in batch, even though I'll take all the data set, I'll repeat till my error will be come to some threshold or minimum. Correct, no?
Yeah, you will repeat until say your W does not change much or your loss becomes close to zero. So it depends on what is the stopping criteria that you give.
Okay. But in this two, which is a computational complex, which will be in general practical used?
So in general, because suppose you have say 100,000 data sets, 100,000 points, right? So computing your gradient of your loss with respect to each of these 100,000 points will be very costly, right? So that is why we do not, when you have a large number of points, we do not do batch gradient descent because it becomes costly. So your batch gradient descent becomes costly. So that is why we do stochastic gradient descent in that case, because you only need to compute this with respect to one point. So here you will run gradient descent for one time. So if we do stochastic gradient descent, you will run gradient descent for each point 1,000 at 100,000 times. So this becomes more costly. This becomes more efficient because you are only looking at gradients per point.
But smaller data set prefer the batch because it will be more
Yeah, if
accurate.
it is a smaller data set and a good CPU or GPU, then you can use gradient batch gradient descent.
What are the advantages of batch actually? The advantages.
So advantage this is because you are randomly sampling a point, right? So this is a random type of algorithm. So each time you may not go in the direction. So sometimes your loss may decrease. Sometimes your loss may decrease, and so on. Because you are computing a point or computing the gradient with respect to each point. So at each time it is not necessary that you will get a gradient which is always in the direction of the minimum. But in batch gradient descent, you are always going in the direction of the minimum. So it will converge fast to the minima in batch gradient descent. But in stochastic gradient descent, sometimes you will go in the direction of the minima, sometimes you will go away from direction of the minima.
Yeah, clear. Thank you.
Okay. So Jitendra was asking if I only want to classify whether two images are same or not. Yeah, then you can use clustering in that case. If you just want to say if 2 points are same or not, then you can say that if they belong to the same cluster, then they are similar. Otherwise, they are not similar according to some similarity metric that you define. Yes. So are you? Yeah. So if you are doing classification task of cats and dogs, you need to have the labels. And once you have labels, it will become a supervised learning task. Yes, you can send me an invite on LinkedIn. In there. So for exam, so the best thing would be to go through the slides and the lectures that have been covered till now, and go through the problems and their solutions that you have done till now, and maybe uh, you might have gone through some textbooks. So I think the exams will ask basic questions. The questions will not be hard, but yeah, I am not preparing the exam questions, so I do not know what the pattern will be.
Adding on that question on exam preparation,
Hmm.
in the assignment, no, we never got any Python related questions. So is it for
Oh,
exam? So we required to prepare Python or not required?
so, I don't think they will ask any coding type of question.
Okay.
It will mostly like they will give you some algorithmic type of, maybe they will give you some pseudocode. What will be the output of this or something like that. We won't get any coding questions.
Okay.
Yeah, whenever you are starting ML, you should no, you should have some knowledge of the theory part because you need to understand what each algorithm is doing. Uh, means a basic. So this is a basic course. It covers most of the algorithms in machine learning. So after this, you can try out different. maybe you can start on different projects, and once you start working on a project, you'll get more clarity. But before that, you'd have at least have some background of what is going on instead of just calling the functions and doing feed and train like that. Yeah, if you even after knowing about gradient descent and the loss function, you need to know about the algorithms, right? Because one algorithm is not applicable to all of the data. So if you want to do a if you want to develop a good machine learning model, you should have some knowledge about what your data is and how you should what will the best algorithm for applying to your problem. So to have those type of intuition, you should have at least some basic knowledge of the course. Of course, you can find online help. There are a lot of blogs which explain how to code this and that, but other than that, you should also have some knowledge about why this works, what will the best way to do that. Yeah, so as a fresher, yeah, once you do some basic course like this course that you are doing, so the next step will be to get started on some project. So you can also go to there's this website called Kaggle where there are a lot of problems that are openly available, and you can participate in those. There are various competitions. You can participate in those competitions, or you can try to develop your own model. So the best way to start is start coding on some project, or get into some competition for that. Yes. So the criteria for selection of the algorithms, it depends on what task that you have. So it actually depends from data to data. You cannot have same model for in all type of problems. So sometimes SVMs may perform better than neural networks. Sometimes decision tree may be better. So it depends. Like you cannot just say in a general sense that this algorithm will perform best for all the cases. So generally, if you have some images or text data, people nowadays go for neural networks, and you go into neural networks, there are these CNNs, RNNs, and all those architectures. So but after other than using those, suppose you have some tabular data, like uh, your data can be represented as a table, so then you can go for decision trees, or you can go for linear regression. So it depends on the data and the task that you have. So in ADA Boost, you always so in ADA Boost, whichever whichever data points are classified correctly, you give less weightage to those, and whichever data points are correct have error in their classification, you give more weightage to those. So basically, you want your model to learn the hard examples better. At each point, at each iteration, you are trying to give more weightage to the hard examples that are not classified correctly by your model till now.
Sir, in week 3, slide number 11.
Okay. Let me go.
Yeah. I have two questions on that. One is actually how training error is increasing initial phase, and that other one, the testing error in the reverse. That's one doubt. And how we do cross validation in the KNN method.
So how is the training error?
In general, we have the training error will reduce the no, with the
Hmm.
number of K increase initially.
Hmm.
So how what are the how it is, why that jump is there, then it is doing. I am not, because in general we see that it's going in reverse direction. I'm not very clear about that. And how we do a cross validation in the KNN method. Other method we know how that the training set and validation will be there. But in the
Hmm.
KNN case, how generally the validation, how it will be done, cross validation, how it will be done.
Okay. So what was the loss for? Okay.
I was not very clear on the cross validation in the KNN. All other places very clear, but KNN
Hmm.
only a good confusion how the data set partitioned and how they do it.
Okay. Let me. Okay, I will get that. So in KNN, your loss is defined by uh, suppose if some point has suppose you have a very uh, if you have a very large K, right? You're talking about 10 nearest neighbors, and then if you are uh, mm, so it is always easy to find a nearest neighbor because you are only looking at one point, right? So whenever you are going to suppose, let's say this is your point that you have, and maybe these are some of the points. So if you are looking at only, and suppose your prediction is
Screen is not
predict,
visible. Are you writing something? The screen is for me. Right? Are you writing the
yes, yes,
computer?
yes.
We are not able to see.
Oh, are you
I'm.
not able to see this?
I have something in my screen, but it's not the update latest. I don't know
Okay,
whether
okay,
I
okay,
have the issue or others are. Oh, for others it's visible. They're telling maybe okay.
okay. Uh, so is it visible now? So suppose, so
It's
can
visible now.
you?
It's visible
Okay,
now.
okay, fine, fine. Suppose these blue points are the. Suppose you are talking about k equal to 1, 2, 3, 4, 5, 6. Suppose your these blue points are the actual uh, the 6 nearest neighbors of the red point, and Once you do some algorithm, maybe because of some error in the algorithm, it will give you the outputs of this, or suppose it outputs your, these black points are the ones that are output. So if your k is say small, if you want to find the nearest neighbor, so it will always find only one point, say it will find this point. So in that case your loss will be less, right? But as you try to as you increase k, as you try to find more and more number of nearest neighbors, so it will be like you are predicting these black points, and the actual one should be these blue points. So as you increase k, this error will increase, right? If you just want to say predict the top 2 points, say, so maybe these are the top 2 points, so the error will be much less because this is zero and this is some error. But if you say you are talking about top 3 points, maybe you will get something like this, so your error will increase in that case. So as you increase k, your error in the near training error will also increase. Is that intuition clear? Because if you increase more points, your errors will get added up, right? So more number of points, you'll have more number of errors that you'll have.
Okay, okay. And so in the when I go for more and more k values, the errors will increase and then stabilize actually. However, our
Yes.
aim is there. However, our aim is to reduce the test error. So
Uh,
even though we'll increase the test error, we'll still continue because we want to. Sorry, even though we increase the train error, we continue the process because we want to come down the test error.
mm-hmm.
That is the aim actually. Okay.
Yes.
And how usually we'll do the validation, I'm just understanding here. This
Mm-hmm.
water data set is a lazy learning, it's basically. So
Mm.
water data set available, we will make some data structures and we'll store the
Yes.
data with us. Okay. And basically two parameters here. One is the k
Mm.
nearest neighbor, what k value, ideal k value. Second, what is
Mm.
the similarity or distance function, which distance function we are going to use it.
Yes.
So with that we'll try and we'll keep it one model. Now we'll
Yes.
give the test data and see the
Mm.
how it behaves.
Yes.
If it's not good, then again I'll go back, again we'll repeat the same.
Yes. For 10, so yeah, you divide your data into 10 parts. You keep one as your test data and other validation data, and you compute the nearest neighbors according to k on your given test data. Then you take another part as the validation data, take the rest 9 as the training data, and you do CV like that.
Okay, so here also, even though it's a lazy learning, we will
Ah,
test it with the test data and we'll fine tune the k and the
yes.
distance function.
Yeah. So basically, yeah, k and the distance or similarity is the one that you want,
Yeah.
the optimum hyperparameters that you want.
No, for me, only confusion here because in the diagram, when it is
Mm.
the case one, it is a very low error, and immediate
Mm.
sharp jump on the high. I was
Yes.
not able to really understand how that much, because I know the k is small means it take a lot of noise.
Yes.
Okay, and when the k increase, the noise should be reduced and it will be more generalized. It
Yes.
will the pattern, but the figure show that that one is, and again
Yeah.
sudden jump will be there. I'm not able to convince
Yeah.
myself
Yeah.
how it happens.
So yeah, the basic idea is like as you include more and more points, your errors will be more and more.
Okay,
But you will go get some sweet spot where your error is like balanced. You don't have much error in the test or validation. Right?
okay, thank you.
Okay. So yeah, you can you will have some criteria, right? So you don't want your error to be more than this, or you'll have some stopping criteria. So it depends what is the k that you have. Suppose you have 10 nearest neighbors and there is no iteration. In fact, you just want to find the optimal set, optimal k value that you want. So once you see that your test loss is low enough, you can say that this is the k that you want. Yes, what do you want to discuss about Bayesian?
Sir, is audible, sir?
Yes, yes.
One more. In the week 3, slide number 40.
Hmm. Yes.
Yeah. Here, that X and Y, basically the two features, am I right, of the data.
No, X and Y are two different data points.
No,
Oh,
I
sorry,
think
sorry. There are two features. Wait a minute. So it depends on in what terms this X and Y are defined.
this is a Pearson correlation, basically.
Yes, yes. Hmm. Yes, you
Because
can say there are two different
yeah,
features. Yes.
why it is confused, no? That because they given Y always will think like a class
Yes,
label.
yes.
But I was asking,
Mhm.
it's a two features basically, X and Y,
Yes, yes.
and we have to select the most non-correlate,
Hmm.
not correlate. Am I right?
Yes, yes.
Right. Okay.
So you want to have the most information. So if two features are correlated, like if I say that I have a feature, say length, uh, and I have a feature, say area. So these two will be correlated. Like more the area, or sorry, more the length, more the area. So it will not give you much information. But if you have some length, area, and some other, say age, so this is not dependent or not much related to the length and area. So you want to have the most information out of all the features.
And in the same slide number 73, I'm not very sure that anywhere any mistake is there in that formula. I'm not very sure. I felt somewhere I don't know. Maybe some I not recollect that I written that point.
So where you do have the where is the doubt in this?
I
So you
think
are looking at algebraic definitions of principal components, right?
yeah.
Hmm.
In that I don't know some comment. I don't know that time when I was writing how only jth vector is used for the z1 selection. Yeah, something like that. Why for principal component? How can you use only one vector, jth vector only? That formula something or
So
so
J, hmm, okay.
xij only jth vector. I'm not understanding.
So there is some issue, I think, because here they are saying J goes from 1 to P, and below they are saying Xj is X1 to. So N is the number of features, P is the number of points that you have.
No issue. I'll check it once again. I'm not recalled exactly what I written that day. It's no issue. I think
Yeah,
it because
okay.
go to previous slides also. Then only you'll get connectivity.
Yeah, maybe because this is not making much sense to me also.
Yeah. And something more on condition independent because some more questions are coming last time also. So more
Hmm.
condition independent how it is in the Bayesian. I'm asking now.
Hmm.
What is the condition independent and how it is calculated and how it is when the formulas comes down.
Okay. So, is it there in any of the slides that I can share?
67, week 4, 67.
Okay.
Condition independent, more questions came last time in the
Mhm.
I think, but the slides are only few. I think only hardly 3 slides are there,
Okay, okay.
but questions are more. So I referred somewhere outside also, but still, if I get some simple method.
Mhm. So basically, so if I say that you have two events, say X, suppose you have two events A and B, so they are independent. If you want to, suppose you want to check what is the probability of event A and the probability of event B occurring together. Probability of event A and probability of event B. So in that case, if A and B are independent, so we can say that this is equal to probability of event A occurring and probability of event B occurring. So this is the basic definition of independence, right? So when you are talking about conditional independence, suppose we want to check, suppose there is another event C such that we want to check what is the probability of event A occurring and event B occurring given that event C has occurred. So in that case, we can say that probability of A occurring given event C has occurred multiplied by probability of event B occurring given event C has occurred. So this is conditional independence. So let me see what is in week 4. So slide number 67, right? Okay. Okay. So this is in Bayesian belief networks. So hmm, there is this line at the end that each node is asserted to be conditionally independent of its non-descendants given its immediate parents. So suppose you have an event A here and some event C occurs, and suppose we have another, say, B here. So here A and B are said to be conditionally independent. So because once event C occurs, only then you can have event A or event B. But probability that event A and B occurs, so then you can write it like this, like what is the probability that event A occurs after event C, that is independent of what probability of B occurring after event C. So that is what is meant by conditional independence in this situation.
If I want to find out what is the probability of A given C, because in that formula, okay, yeah.
Yeah, this will be known, because this will be known at some point of time. But suppose you want to check what is the probability of A and B occurring given C, then you can do this.
Why I'm asking this question? Sometime, no, even though if they give the probability, I can't able to calculate if I don't get the Bayesian graph. So somewhere the graph dependency is there.
Yes.
So what are the cases where even though I got the probability, the graph is had required to calculate for me? Such cases.
Mm-hmm. So I think the graph will be given to you. So you just have to look. So suppose you have this graph, right, where A and B share the same ancestor. Then you can assume that A and B are independent in this case. or there will be some other, so A is dependent on C, B is dependent on C. But if I have some, say, E is not dependent on B, E is independent of P, we can have these assumptions.
Now E is dependent on A. It's like a trans dependence, correct? No, C
Yeah,
A.
hmm, E is dependent on A in this case. If A occurs, then C occurs. Sorry, E occurs.
And here the E is conditional dependent on C. Is it like
A
that?
is
Here also
conditional, yes, is conditional
conditional
dependent.
C.
Hmm.
A
Because
is
if C occurs, event A will occur with some probability. So you will need this A after C.
okay. Thank you.
So week 4 page 9, there is no example question here. Do you mean page 10? Discrete random variables. So can you explain what doubt you have, so I can get it? So these are basically examples of random variables, discrete random variables. So that means if you have a random variable x, so what are the possible values it can take, right? So suppose your random variable is whether if you toss a coin, your random variable is whether your output's a head or tail. So then the value of your random variable can either be h or either can be t. So in this case, suppose you have two dice. So dice is six-sided, right? So the first, so suppose your random value is sum of the value of dice, right? So in that case, on the first die, maybe you have some value between 1 and 6. In the second dice, you will have some value between 1 and 6. So if you sum both of these up, so your random variable x will be the sum of these two variables. So either you can get something from 1 in the first dice and 1 in the second dice, that is 1 plus 1 is 2, or you can have a lot of combinations, and at last you can get something like 6 and 6. So your random variable x can have values from 2 to 12. So, and again in the second example, it is said that x is a random variable with arity k. So that means it can, suppose you have given k to be 100, so that means your x can be any value between 1 and 100. So uh, those are the examples given in this slide. If you have any other questions, you can ask those. So in page 54 of week 4 slides, so basically you are given the uh, table on page 7, sorry, page number 52, right? So according to that, you have this probability. So uh, let me share my screen. So uh, you are given this table, right? So you have to look at these probabilities. So let's look at this probability that outlook is sunny given that play is yes. So here you look, so here are 14 examples, and out of these 14 examples, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them are yes. So this becomes a conditional probability because you do not have to look at the probabilities out of all the examples. Because you have this condition that play equal to yes, you only have to look at the probability out of all those points whose output is yes. So here we want to look at where do you have that output is sunny given that play equal to s yes. So now we are looking at only these red points, and this is your outlook, and you want sunny. So you have this as the sunny given that it is a yes. This as sunny given that this is yes, and the others do not have this condition. So that out of 9 times you have 2 events where your outlook is sunny given that your play is yes. So you can apply the same methods to all of the other probabilities that are given here. So this is the prior that you have, that given the data set, you can play tennis 9 out of 14 times, you cannot play tennis 5 out of 14 times. So your map rule was your calculating the maximum posterior. Posterior was the RHS of the, sorry, LHS of the, so it is the output of the Bayesian formula that you had. So this is your posterior. So you have to calculate a maximum of this. So for that, your formula comes out to be like this, as given here. Is that clear?